Alright, today we're going to talk about Riemann sums. Now, we're going to get a little background here. There's a property that says a definite integral. So far we've talked about indefinite integrals. In other words, the integral from a to b of f of x dx equals the area under the curve. We've talked about this a little bit already. Essentially what they're saying is that if we have a curve, and it looks something like this, and if we integrate over an interval a to b, that the definite integral is the area between the curve and the x-axis. That's important to realize, because now what we want to do is we want to figure out how can we find that area. In the past we've counted squares and that sort of thing, and we may have looked at some basic Riemann sums in the past. But what a Riemann sum is if we look at a graph and we look at an integral from a to b, and what a Riemann sum does is it makes rectangles of equal width and I'll pretend they're equal width. Right. All our rectangles have width delta x, and they have height y, or they have height f of x. Right. So the area would be the sum of the areas of those rectangles. Right? In other words, we have a finite number of rectangles, and if we find the areas of all the rectangles, add them together, and we have the area under the curve, or an approximation of the area under the curve. Now, what I've drawn here, this is called a lower sum. Okay? Because we're using the lowest point on the graph as the top of our rectangle. This also would be called a left-hand sum. Because all my rectangles start on the left and go to the right. Believe it or not, there are some that call this a right-hand sum. I've always heard it called a left-hand sum. So that's what that looks like. Let's take a look at another one. Let's take a look at a graph that looks kind of like this. Here's A, here's B. Now what they might do is say that something like n equals 4. In other words, we're going to have 4 equally spaced rectangles. Something like that. We're going to divvy them up like that. And there are 3 basic types of Riemann sums and one special sum that isn't really called a Riemann sum, but it is. The first one we looked at was the lower sum, or the left-hand sum. Now, the next type would be what's called an upper sum, where we use the upper point of the rectangle. And this one looks like it does a fairly good job. And again, it's always the change in x times the height of the rectangle, and that gives you the area of one rectangle. then add all four of them up, and that would give you an approximation of the area. And this is what I called an upper sum. Yep. And in this case, it would also be called a right hand sum, because all of our rectangles start on the right side of the graph, or the right endpoint is the height of the graph. Okay. So that's the second type of Riemann sum. Now the third type wow, that's a horrible axis. Let's say we had a graph that looked, oh, I don't know, let's make it go like this. Here's B, here's A, and let's stick with n equals 4. Right. So we want to divide this into 4 equal rectangles. Okay. This time, however, what we're going to do is, instead of using a left-hand sum or a right-hand sum or an upper sum or a lower sum, oh, we didn't talk about lower sums yet. We'll do another one yet. We're going to do a midpoint sum. Midpoint. Which means that we go up to the middle of our interval, and that's how we make the rectangle. Right, and this one's pretty special. It actually works out kind of nice. Look at that. Fourth one works out good. That's a midpoint sum, right? We just go to the midpoint, go up to the graph, right? We get f of x, and each of our changes down here are the same. So again, the area of one of those rectangles is delta x f of x, or f of x delta, yeah, f of x delta x. Right? Okay, so the height times the change in x. Nothing more to it. Okay. A lower sum. Let's look at a lower sum. Okay. Let's see. Let's have a graph that looks like that. Another one of these. Here's A. Here's B. And we want the lower sum. Again, we're going to let n equal 4. This time what we do is we go up to the lowest point on the graph, come across like that. This one, it's going to look like this. This one's going to look like that as well. And this one's going to look like that. Okay, it's a lower sum because we're using the lowest value on the interval, or the lowest endpoint. Again, it's not a right-hand or a left-hand sum because over in this area we're looking at the left side, and over here we're looking at the right. Okay? So, one more of these things to look at, and it's actually called trapezoid rule. Okay? We look at our nice little function. Looks like that. Here's A, here's B. We use n equals 4. This time what we do, we split that into, what we're going to do is we're going to come up and we're going to make trapezoids out of each of these things. And we want to find the area of each of those trapezoids. Well, remember that the area of a trapezoid is the height, and this time It's delta x for each of these things because we have equally spaced intervals. And that's times the average of the heights or the lengths of the parallel sides of our trapezoid. So that would be like y1 plus y2 divided by 2. Okay. And that would give us the area of the first trapezoid. And we would use a similar method to find the others. Right? It's always divide by 2. We've got two lengths and we're looking for the average. Alright, well, I'm approaching 11 minutes here, so I'm going to let you go because I promised I would keep it short. We'll talk about this some more on Monday. Thank you.